Hello everybody, welcome to my class Physics 100 for international students. Today we will talk about the temperature and heat. After taking this course, students will understand the basic concepts of heat and temperature and be able to calculate some thermal properties of matter like temperature, specific heat, heat conductivity, and phase transition. By learning about temperature and heat, you can answer why you need to put a gap between two rails in a railway. So, what is temperature? In our daily life, the term of temperature is used to describe the degree of sensation of our skin in response to cold and hot. When you touch the ice cube, we set this as a cold temperature. But when you touch the hot pan, you said that this is the high temperature. Thermal equilibrium. If you see this picture on the left side, you have two objects. First with the higher temperature and the second one with the lower temperature. If those two objects with different temperatures are brought in contact, eventually after some time, those two objects will reach a single equilibrium temperature. We call those two objects is in equilibrium with each other. And if these two objects are brought in contact with a third system, they will also reach a single equilibrium temperature. So the principle of thermal equilibrium is very important. For example, for temperature measurement device. So when you try to measure the temperature of an object, you put the thermometer on that object and you have to wait until the thermal equilibrium between that object and the thermometer is reached. For measuring the temperature, there are various thermometers that you can use. You can use the scale using degree of Celsius or Fahrenheit, or you can use a digital thermometer with some sensor or thermocouple inside. You can convert from one scale to another scale by looking at the boiling point and the freezing point of each scale. You can use the equation below on the right bottom corner. T1 minus T1F. So suppose if 1 is Celsius scale, so if the temperature in Celsius is T1 minus the freezing point of Celsius, which is 0, divided by T1B minus T1F, the boiling point of Celsius scale, which is 100, and T1F, the freezing point of water in Celsius scale, which is 0, equal to, suppose T2 is the temperature in the Fahrenheit scale, T2 minus freezing point in Fahrenheit scale, 32 degree, divided by T2B minus T2F, the boiling point in Fahrenheit scale, 212, minus T2F, the freezing point in Fahrenheit scale, which is 32. So you can look in here in a yellow box here, C divided by 100 equal to F minus 32 divided by 180. In this example, you are asked to find 50 degrees Celsius in a degree of Fahrenheit. So again, the degree Celsius is C divided by the whole scale of Celsius, which is 100, the boiling point 100 minus the freezing point 0 degrees Celsius, equal to the corresponding temperature in Fahrenheit, F, minus the freezing point of Fahrenheit scale, which is 32, divided by the whole scale in Fahrenheit from 212, the boiling point, minus 32, the freezing point, which is 180 degree in Fahrenheit. So solving this equation, then you can find F is equal to 50 times 180 over 100, or this is just 9 divided by 5 plus 32. So you got the corresponding reading in Fahrenheit scale is 122. So 50 degrees Celsius equal to 122 degree Fahrenheit. Thermal expansion. An object will expand due to a heating and shrink due to a cooling. So for example, the power cable will expand during the day and shrink during the night. So you need to use a proper length. So when it expands, the cable not touching the ground, and when it shrunk, it won't break the cable. The other example is the glass window installation. So when you install the glass on the frame, you need to consider a gap between the glass and the frame, because if there's no gap during the hot day, when the glass expand and there's no gap between the glass and the frame, you will break the glass. The thermal expansion of the object, delta L, depends linearly on the change of temperature, delta T, depends linearly to the initial length of this object, L naught, and depends linearly on the coefficient of thermal expansion. Alpha, or the coefficient of thermal expansion, depends on the type of the object. Various objects has different alpha. For example, wood, steel, aluminum, bronze, they will have a different alpha. When delta T is positive, means that the object experience an increasing temperature, delta L will be positive too. So we will have an expansion of the object. But when the delta T is negative, delta L is also negative. Delta L negative means that we will have a shrinkage. So instead of getting longer, the object now is getting shorter. We have three different expansion. First, one-dimensional expansion, delta L, when the object is getting longer or getting shorter. And the next one is two-dimensional expansion, when the object is either getting larger or smaller. The area of the object getting bigger or smaller. And the next one is the three-dimensional expansion, or delta V. So for each dimension, we have different equation, but the only difference is actually the coefficient alpha. Instead of alpha, one-dimensional coefficient of linear expansion, for the two-dimensional we have beta. Beta is 2 alpha. Why? Because we have expansion in two directions, suppose x and y. And the change of area, delta A, for two-dimensional expansion depends linearly on beta, the initial area A0, and the change of temperature delta T. For the three-dimensional expansion, we have a change in volume delta V. Delta V equal to gamma, the coefficient of three-dimensional expansion. So because gamma is three-dimensional, gamma is 3 times alpha. So delta V is equal to gamma times V naught, the initial volume, times delta T. When the temperature of the object is increased, usually the object will expand or the volumes getting larger. But that's not the case for the water. When the temperature of the water increases from 0 to 4 degrees Celsius, instead of expanding, water shrinking. The volume of the water is decreased, so the density is increased. So for the same amount of volume, water getting heavier. So you see in the picture below on the left side, the water at 4 degrees Celsius stay at the bottom because it's heavier as compared to the water at 2 degrees Celsius or 1 degree Celsius. And the surface of the lake is covered by ice. Ice has the smaller density as compared to the water. But during the normal time, during the summer, when the temperature is above 4 degrees Celsius, water behaves normally. So when the temperature is higher, the volume is getting higher too. That's why water at 8 degrees Celsius has more volume as compared to the water at 7 degrees Celsius. This anomaly is very important in life survival of creatures in a cold environment. During a cold winter, water is located underneath the ice sheet due to its density. That's why people do ice fishing during the winter. So even you see the lake is covered by ice, but below that ice you will find water. Not it's a freezing water, but it's not ice. So what is heat? Heat is the amount of energy transferred from a higher temperature object to a lower temperature object. So if you boil the water, the heat is transferred from the flame to the pan. That's why you can boil the water in the pan. The amount of heat needed to change the temperature of an object is Q equal to mc delta T. Q, or heat, linearly depends on the mass of the object, and C, the specific heat of this object, and delta T, the change of temperature experienced by that object. Heat is energy. The unit for heat is calorie. 1 calorie equal the amount of heat needed to increase the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is equal to 4.19 joule. When an object is exposed to the heat, there are two options. You can only have one option at a time. You cannot have both options happen at the same time. So when a substance is exposed to the heat, either the temperature of the substance is changed, but the form of phase remains constant, or the form or phase of the substance is changed, but the temperature remains constant. When the temperature of the substance is changed, so you have delta T, and the heat needed to increase the substance to that particular temperature is Q mc delta T. In this process, the substance is still the same. If the substance is solid, it's still solid. When the substance is liquid, still liquid. And for the next one, the form of the substance is changed. So for example, if initially the substance is in liquid, now change to gas or steam. At this time, the temperature remains constant. So that's why we have a boiling point. Boiling point is a particular temperature when the object changes its phase. The heat needed to change from one phase to another phase, Q, is equal to M times L, where L is the latent heat. Latent heat is the energy needed to change from one phase to other phase. State of matter could be solid, liquid, gas, or plasma. Plasma is also gas, but gas of ions. The heat needed for transformation from one phase to another is Q equal to mL, where L is the latent heat. Latent heat is the energy needed to change from one phase to another phase. For example, melting heat of ice, actually the energy needed to change the phase from the solid water into liquid water. Solid water means ice. So if you want to change 1 gram of ice into 1 gram of liquid water, you need 80 calories per gram. This is a lot higher as compared to the specific heat of water. To increase the temperature of water by 1 degree Celsius, you only need 1 calorie per gram per degree Celsius. But to change 1 gram of ice into 1 gram of liquid water, you need 80 calories per gram. The vaporization heat is the energy to change from the liquid into a gas, and you need a lot higher as compared to the melting heat. To change 1 gram of liquid water into 1 gram of water steam, you need 530 calories per gram. In an isolated system, heat is transferred from a higher temperature object to a lower temperature object. In this isolated system, the energy is conserved, means that the heat absorbed by the lower temperature object equal to the heat emitted by higher temperature object. This is called as a Black's rule. Using heat equation, we can analyze the phase transition from one state to another state. So, for example, here we want to convert minus 40 degrees Celsius of ice into 120 degrees Celsius of vapor. First, you have to increase the temperature of ice from minus 40 degrees Celsius to 0 degrees Celsius. The heat needed for this process, Q1, is mc delta T, where m is the mass of the ice, c here is the specific heat of ice, and delta T is the change of temperature, which is 40 degree. The next step, now the ice already at 0 degrees Celsius, you need to convert it into liquid water. The heat needed for this Q2 is equal to mL. M is the mass of the ice and L is the latent heat of water. You see that we have a red line and green line. Red line means the temperature is increased, the phase is the same. Green line means that the temperature is the same, but the phase is changed from one state to other state. Once the ice already in a liquid water form at 0 degrees Celsius, now we want to increase this water temperature from 0 to 100 degrees Celsius. The heat needed for this Q3 is mc delta T, where m is the mass of the ice, in this case already in the water form, m is mass of the water, c is the specific of the water, because now we have a water, times delta T, the change of temperature. From 0 to 100 degrees Celsius, the change of temperature is simply just 100. Once the water already reached 100 degrees Celsius, now we need to convert this water into a steam or vapor. The heat needed for this Q4 is equal to m times L, where L is the latent heat or vaporization heat of water into a gas. Once the water already in a form of steam at 100 degrees Celsius, now we need to increase the temperature into 120 degrees Celsius of vapor. So the heat needed for this process, mc delta T. M is the mass of the water, C is the specific heat of the water vapor, and delta T is 20 degrees Celsius. So you have to sum them up to get the total heat needed to convert minus 40 degrees Celsius of ice into 120 degrees Celsius of vapor. The latent heat to change water into vapor is not just at 100 degrees Celsius, but also at room temperature. This process is called as evaporation. The evaporation happens in our daily lives. So for example, water in the sea and exposed to the sunlight will evaporate and create the cloud, and after some time the cloud getting heavier and we will have rain, and the rain goes to the ground and then goes to the river and come back to the ocean. This cycle is very important in our life. The heat can be transferred from one object to other object by three means: conduction, convection, and radiation. Conduction is the transfer of heat by microscopic collision of particles within an object. Microscopic particles means atoms, molecules, or electrons. The rate of heat transfer in conduction is formulated as H equal to delta Q over delta T, and linearly depends on the type of material or thermal conductivity K, linearly depends on the difference of temperature delta T, and inversely proportional to the length of the object, and proportional to the cross-sectional area of the object. So the bigger the cross-sectional area, the higher the conduction rate. The longer the object, the smaller the conduction rate. Convection is the transfer of heat by the movement of groups of molecules within fluids such as liquids or gases. So in convection, there is a movement of the medium. This is in contrast to the conduction, where the medium is not moving. The example of convection is the boiling water. So when you boil the water with higher temperature at the bottom will move to the surface, and the water in the surface will move to the bottom, and we will see this current, convection current, happen during the boiling water process. In radiation, the heat is transferred from one place to the other without any medium. The radiation rate linearly depends on the temperature to the fourth, the radius of the emanating or radiating body, and linearly depend on the constants E, coefficient of emissivity, and sigma, the Stefan Boltzmann constant. So the example of radiation is like sunlight, or if you have a bonfire and you're sitting not far from the bonfire, you can feel the heat. Thank you very much for listening to these lectures. See you until the next lecture. Thank you.